Greetings! Today we're going to talk about superposition for AC. Superposition is a very useful theorem as it allows you to find voltages and currents in circuits that have multiple sources, multiple current sources and voltage sources. Let's start with a fairly simple circuit. Now, superposition does require that the circuit be a linear bilateral network. Now, as long as we're using capacitors, resistors, inductors, that will be the case. So we'll start with a fairly straightforward circuit here. We'll begin with a simple voltage source, a resistor, an inductor. We'll tie this into a capacitor and a second voltage source. First source, we will make 1 volt at an angle of 0. Reference polarity plus to minus top to bottom. Second source will make 2 volts at an angle of 90 degrees. Same reference polarity. The component values will just make 100 ohms, J200 for the inductor, and minus J300 for the capacitor. Now, one possible method of solution for this particular circuit is through the use of source conversion. You could do a source conversion on this first source with the 100 ohm, replace that with a current source, which would look something like this. The resistor, of course, would be in parallel. The second source and the associated capacitor would also be translated into a current source. That would give you something like this. Here's the capacitor. And of course the inductor is at that same node. We have this. Now, what you would notice about this is a completely parallel circuit. So if we could find the impedance of those three elements, the 100, J200, and minus J300, and then combine the two sources, we could simply use Ohm's law to find the voltage across the inductor. Now, once that's found, we can apply that back to the original circuit. Knowing that voltage and using Kirchhoff's voltage law, we could find the voltage across the capacitor, the voltage across the resistor, and consequently find any branch current that we were interested in as well. So to find these two sources, of course, we would have to find the short circuit current, in which case we would replace this section with a short, and what we would find is the 1 volt source would drop across the 100 ohm. That would give us a equivalent current of 10 milliamps at an angle of 0 degrees. Similarly, on this end, we would short out this section and just have the 2 volt source dropping over the capacitor of minus J300, and that would give us a current of 6.67 milliamps at an angle of 180 degrees. Now, the combination of these three RLC components, we could simply do a reciprocal summation, 1 over 100 plus 1 over J200 plus 1 over minus J300. Take the reciprocal of that, we'll get the total Z. So the total Z over here will equal 98.64 ohms at an angle of 9.46 degrees. Now notice this is a slightly positive angle. That makes sense. The inductor is a smaller value in parallel with the capacitor, so we expect the combined impedance to be slightly inductive. Of course, the resistor is the smallest of the three, so we don't expect a very large angle. So this seems to make pretty good sense. Now, the two currents, when they combine, notice that this current source is 180 degrees out of phase with this current source, which basically means we simply subtract 6 2/3 milliamps from this 10 milliamp source. That's going to give us 3 1/3 mils. So our completed current, our total current, will simply be 3.33 roughly milliamps at an angle of 0 degrees. Now, using Ohm's law, we pass that current through this impedance, and we wind up with a voltage across the inductor of 0.3288 volts at an angle of 9.46 degrees. Okay? That's the voltage that appears across the inductor, and as I said, we could now use KVL to find those other voltages, currents, and so forth. All well and good. The problem here is this technique will not work on all circuits. There are a great number of circuits where simply doing a source conversion is not going to help you. So in superposition, the idea is that each source can be treated by itself. In other words, we'll find the contribution of that source to a particular current or voltage. We'll find the contribution of the second source, the third source, and so forth, and then combine them together, being cognizant of the current directions and the voltage polarities. So we will generate as many circuits as we have sources. Every single source that we consider, all other sources will be replaced with their ideal internal impedance. So that means for a voltage source it'll be shorted, for a current source it'll be opened. In this case we have two sources, so we'll have two circuits. First we'll consider the 1 volt source. That feeds the 100 over here. Here's the inductor coming down. Now, the second source is going to be replaced with its ideal internal impedance, a short. So this point is basically shorted to here, which means that capacitor is essentially in parallel with the inductor. This is what we're looking at. All right, so I got a minus J300 there. Now, to find the voltage across the inductor, all we really have to do is find out what this impedance is and then do a voltage divider. So this impedance, we could use the product sum rule, J200 in parallel with minus J300, and that'll give us 600 at an angle of 90 degrees, or if you prefer, J600. I now do a voltage divider on that, so that would be 1 at an angle of 0 times the item we're interested in, which is 600 angle 90, divided by the total, which would be 100, plus this impedance. Probably easiest to write that here is J600. And when we calculate that out, the voltage across the inductor as produced by that first source acting alone will be just under a volt, 0.9864 volts at an angle of 9.46 degrees. Now we turn to the second source. We do the same thing. We short the first source, redraw the circuit, see what we get. So here we have our 2 volt source, 2 at an angle of 90. That's going to feed into the capacitor. And the inductor's coming down, like so. And finally we short this voltage source, which takes this end of the resistor and brings that down to our common point, in other words, in parallel with the inductor. And I'll just draw that like so. Well, we have the similar situation that we had before, which is basically, if we can find this impedance, we can do a voltage divider once again, find out what this voltage is, and then we'll just add the two when we get done. This happens to work out, this impedance happens to work out to 89.44 at an angle of 26.6 degrees. Again, that makes sort of intuitive sense. It's inductive, so we do see a positive angle here, and again, the 100 ohm resistor is going to dominate, so it's not going to be a large angle, it's going to be less than 45 degrees. That seems to make sense, right? This happens to be equal to 80 plus J40 if you do it in rectangular form, which would be handy when we do the voltage divider over here. So the voltage divider would basically say take 2 at an angle of 90 times the thing you're interested in, which is this, I'll write it as 80 plus J40, and then divided by that plus the minus J300, so that happens to be 80 minus J260. And that voltage will work out to 0.6576 volts at an angle of minus 170.5 degrees. right? So this is nearly out of phase with this, right? It's not exactly perfect, but we probably have a little bit of round-off error here. But in either case, when we combine these two things together, right, you just add these two things together, we will end up with, big surprise, 0.3288 at an angle of 9.46 degrees, right? If we were to carry all the digits out, that is. And we see that, hey, these two values are identical. Beautiful, right? Now, in this particular case, the two voltage sources happen to produce reference polarity on voltage like so across the inductor, right? Plus to minus. We just straight add them up. Everything's very simple. We could also use this on current, not just voltage. So for example, if I was interested in finding the current through the, let's say, the 100 ohm resistor, right, we could do the same sort of solution over here. It'd be a little bit different. One straightforward way of doing that would be to, again, find this impedance. And then we could just say, okay, what's 1 volt dropping over 100 plus this 600 at an angle of 90? That would give us the current flowing through here. But important to note, that current reference polarity would be like this, right? Because, again, our polarity on the source, plus to minus, top to bottom. So when this is going positive, positive half wave, that's the direction of the current flow that we would see. Now, I'll turn around and do the same thing over here. I want to find the current going through the 100. So this polarity, plus to minus, would produce a current going through the cap like so, and that will split at this node, part down through the inductor, part down through the resistor, like so. The technique would be similar. We could take the minus J300, add that to this impedance, the 89.44, divide that into the 2 volts at an angle of 90 degrees, and we could find that current. However, this current is effectively flowing in the opposite direction compared to this current, right? We can see this is flowing from this node right to left, whereas in this case, it's flowing in the opposite direction. It's flowing from left to right. So this current would have to be subtracted from this current. This is a question that's very often raised. Which one is subtracted from which? Well, it all depends on how we define it to begin with. So if I'm going to define the current direction like this, from left to right in my original diagram, then that becomes the positive direction. Anything fighting that becomes negative. So in this case, we would take this current, we would subtract this current, that would give us the result. We could just as easily define, or assume, if you will, the current's going in this direction, in which case, all right, we would take this as the positive, we would take this as the negative. All right? And we just follow through, sum the pieces together, off we go. Now if I have 3, 4, 5 sources, this will simply be replicated. If I had 3 sources, there would be a third circuit here. We would figure out the voltage or the current that I was interested in. We could actually figure out multiple things, different currents, different voltages. And we would just follow through, again, being cognizant of what the current directions and what the voltage polarities happen to be. Okay? You just follow this, and everything will work out really nice. Now, not every single possible circuit can be solved with superposition. There are certain sorts of configurations that superposition will not help you with, and we will look at those coming up. However, this is a really good technique. It's a fairly straightforward technique. It can be a little busy. Granted, if you had 6 sources, you'd have to have 6 equivalent circuits, but it all does work. Again, the caveat is this must be a linear bilateral network. That also applies for the functions. In other words, we can use this for things like currents and voltages, but you can't use it for power, at least not directly. In other words, I couldn't say, hey, I want to find the power in this 100 ohm resistor. Let me find it in this circuit, and then I'll find it in this circuit, and I'll add the two together. That will not work. Power is a square law function, right? Power is proportional to the square of voltage or the square of current. So that's not going to work. Here's a good way to remember that. In this particular case, these two currents are going in opposite directions. Now, if you were to just calculate the power, let's say by using I squared R here and I squared R here, well, the sign, whether it's positive or negative, disappears, right? When you square it, a negative current turns into a positive squared value. So it wouldn't really make any difference on your calculation, right? So that tells you immediately, yeah, that can't work. In other words, if I had swapped polarities of things, if the current was going this way versus this way, I'd get the same result as long as the magnitude was the same. So how would you find power? Well, what you would do is basically what we just did. You would have to find either the current or the voltage of interest through this process. Then once you get the final value, like for example, if we found out this was half a volt after doing these summations, then I could take that final value, use power law, and calculate what the power is. And there you have it.